So far what we learned is that if I have a circuit, if I have any system in general, I can write the transfer function, which is the ratio of the output to the input, right? And as it turned out, if I look at my input and look at my output, these two can be represented using a polynomial. They have like different degrees, but they're still like a polynomial, right? We said if we have a polynomial, we can always decompose the polynomial into its root, right? But if you look at the roots are either complex or real. If they're real, we got no issue. But if they're complex, to get rid of like complex numbers, we're going to try to combine these complex roots so that it's not complex anymore. We use the fact that if z1, which is a complex root of like this polynomial, because all the coefficients of like this polynomial is real, z star, which is the complex conjugate of that root, must also be another, right? We use that fact and we combine the complex roots. So what we ended up getting was a decomposition that had all my real roots and all my complex roots combined together, written as a quadratic function, right? So recall, we can always write our transfer function as h of s some constant k, some poles or zeros that are happening at the origin. Let's just say the multiplicity of that is n, times all the real roots that we have. So I have s divided by z1 plus 1 to the power of L1, and all the complex ones, which I can write it in terms of 1 plus 2 psi 1 tau 1 s plus s over tau 1 squared. Let's just say to the power of L2. And similar terms, right? And I can do the same thing for the denominator. So I can write it as s over p1 plus 1 to the power of h1 times the quadratic ones. So it's 1 plus 2 psi 2 tau 2s plus s over tau 2 to the power of 2 h2 and similar terms. So that was my decomposition. And we said there are some advantage to decomposing my transfer function into a form that looks like this. So let's define quickly like what these terms are and what the advantage of like this definition is. This basically form of writing is. First of all, this is some constant. So this is some constant. If I'm able to decompose it this way, this term over here tells me if I have 0 or pole at the origin. So this tells me 0 or pole at the origin. Right? This term over here, which is a representative of a simple 0, tells me I have a 0 at z1. So that is a simple 0 at z1. And this term over here, that is basically the quadratic 0 that I have. Right? I can say the same thing about this term over here. That tells me I have a simple pole at P1, and this term over here that tells me I have a quadratic pole. Right? So the main advantage of this is that by looking at this transfer function, I can immediately say, these are my zeros, these are my poles, and what type of zeros and poles I have. Right? But we said there is a lot more to this H of S. If I'm able to like decompose this H of S in terms of like this multiplication, I can just simply find the magnitude and the phase of this. Right? The magnitude is not quite useful, but the phase is very, very useful. Right? Because this H of S, remember that S is always like I omega. So this S is I omega. Therefore, this H of S is a complex function. Right? So if I want to find the phase of like two complex numbers that are multiplied, I know the phase of the multiplication is the summation of both phases. And if I divide two complex numbers, I know the phase of the division is the phase of the numerator minus the phase of the denominator. Right? So by looking at this decomposition that I have a bunch of like multiplication and a division, which means I can simply just find the phase of this H of S. Right? So I know the phase for H of S is phase for this K, which we know it is 0. Why? Because it's just a real number. There is no phase to it. Right? Plus the phase for this S to the power of plus or minus n, plus the phase for this term, S over Z1 plus 1 to the power of L1, plus the phase for the quadratic form, 1 plus 2 psi 1 over tau 1 S plus S over tau 1 squared. Or whatever other term that I have, minus these because they actually happen to be at the denominator, right? So it's minus phase of S over P1 plus V1 plus 1 to the power of H1 minus phase for the quadratic, 2 psi 2 tau 2 S plus S over tau 2 squared to the power of H2. Minus other two, right? So it's pretty good for the phase. But we still got issue if we want to find the magnitude of this H of S. Because the magnitude of H of S is the magnitude of like all these terms multiplied. And plotting the multiplication is quite difficult. We said the only way that we can get around it is to change our scale. So instead of looking at it on the linear scale, which is this function, we can actually look at it on the log scale. Right? And we define the devious scale to be 20 times log 10 of the magnitude of H of S. As soon as we look at the 20 times log 10 of magnitude, then all these multiplications become summation, and that division becomes subtraction. That's just a property of log. Right? So I can find 20 times log 10 of magnitude of H of S, which is going to be 20 times log 10 of magnitude of this K, plus 20 times log 10 of magnitude of this S to the power of plus or minus n. But we know if I have some number to the power of m, if I take a log of that, I can pull that power out and simplify it. So I can write this as plus or minus 20 times n log 10 of magnitude of S plus 20 times L1 log 10 of magnitude of S over Z1 plus 1 plus 20 times L2 log 10 of magnitude of this quadratic form. Tau 1 plus S over tau 1 squared plus other terms minus 20 times H1 log 10 of magnitude of S over P1 plus 1 minus 20 times H2 log 10 of magnitude of this quadratic. Right? And other terms. Now my life is a little easier, right? Because as soon as I know how to plot each term, I know how to plot the whole thing. I just need to add them on top of each other, right? But it is still not good enough. Because if I look at, for example, this term over here, if I look at the magnitude is the square root of 1 plus omega squared divided by Z1 squared. So it's not an easy function to plot, right? So the idea is, instead of plotting the actual function, let's just approximate that function by a linear function, right? So we're going to have to approximate each term that we have over here by its linear approximation. How do we usually get the linear approximation? It's a Taylor expansion, right? Taylor expansion always gives us a linear term plus the higher orders. So we can forget about the higher order, right? Good news is we don't really have to write the Taylor expansion. I'll give it to you. I'll tell you exactly like what those things are. You can just apply it, right? But the idea here is that I still cannot plot this 20 times log 10 of h of s. I have to approximate it. And I have to approximate it by a linear function, right? So the idea here is to approximate each function by a linear function. Right? This is a linear approximation. And if each term over here is approximated by a linear function, the entire function is going to be piecewise linear. Right? So let's just see how we can actually plot each term. I already gave you like the table. I'm going to repeat that table one more time. Just make sure we all know what it is. So let's just say this is my table 2. This is the term. This is the magnitude, which is 20 times log 10 of the magnitude. And this is the phase. I have to be able to plot every single term that I have over here, right? Let's start by the constant. Let's just say I have some constant k. What is the 20 times magnitude of a k is a constant? It is still a constant, right? So if I have this omega, this is going to be 20 times log 10 of absolute value of k, right? What is the phase of a constant? It's always 0, right? So if I plot it, it is 0, right? Falls right over here, right? Keep that in mind. What we're doing here is that we're going from a linear scale to the log scale. So my omega axis is no longer 0, 1, 2, 3, 4, right? It is 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and so on and so forth. That's a semi-log, basically planed out, right? We said we can have poles or zeros right at the origin, right? So let's look at the 0 at the origin of order n. So this is 0 of order n at the origin, right? We said if we're going to plot this, the magnitude, which is 20 times log 10 of this magnitude, is going to look like this. This is 1, this is 20 times n dB. Why is that? Because we know if we have a 0, it should go up. And therefore, the slope of this line is going up. And we know the slope is going up by 20, right? But since it's being repeated n times, so I have to add that n times. That's why the slope over here is like 20 times n dB, right? What is the phase here? Again, the phase here is the phase of I. What is the phase for I? It's 90 degrees, right? But since the order is n, it means I have to add this n times, right? So the phase over here would be 90 times n, right? How about if we have a pole of order n at the origin? So I have 1 over I omega to the power of n, which is a pole of order n at the origin. We know since it's a pole, it has to go down, right? And since it is 1 over exactly this function, so it should be similar to this function, but that's going down, right? So it would look like this. This is omega. This is 20 times log 10 of the magnitude. So it's going down with this slope 20 times n dB, right? What is the phase? Again, the phase is the phase of 1 over I, which is the same as negative I, right? Which is minus 90 degrees. Since I'm repeating it n times, so I have to add it up n times. So therefore, the angle here would be negative 90 times n degrees, right? So far, we talked about these two. Now we got to talk about the simple 0 that's happening at this Z1, right? So if I have again, this is my term. This is the magnitude, 20 times log 10. And this is the phase. So if I have I omega divided by z, z1 plus 1 to the power of n, what I know is I have a 0 at z1 of order n, right? Again, this is a simple 0, so I know it has to go up by 20 dB. But since the z is not 0, I'm going to have like some breakpoint. And that breakpoint is happening exactly at this z1. So if I look at the magnitude, this would look like this. This is Z1, and that's going to go up by 20 N dB. Right? If I look at the phase, it turns out the phase looks like this. 10 times Z1. So it is 0 degree over here. Over here, it's going to be 90 degrees times N. And over here is 45 times N degree going up. Yes?
Is it 10 times Z1 or should it just be Z1?
No, 10 times Z1. Z1 is like somewhere in between. Yeah. Doesn't really matter. What matters is that like I'm going to go up by 45 degrees. That's what's important. Right? Again, I can do the same thing for the pole. So if I have 1 over I omega over P1 plus 1 to the power of N, what I know is that I have a pole at P1 of order N. Right? Which as soon as I'm talking about a pole, I know I have to go down. Right? So if I go down, this is what I get. Again, I have my breakpoint right at P1, and that goes down by negative 20 times N dB. Right? And the phase, I know it should be this phase flipped. Right? Because it's exactly like this one, it's just on the denominator. So if I look at the phase would look like this. So I have P1 over 10, and P1. So that is 0 over here. That is 90 degrees over here. And it is negative 45 times N degree. Right? All I got left is just the quadratic ones. If I know how to plot the quadratic one or approximate the quadratic ones, then I know how to approximate the entire H of S on devious. Right? So let's quickly go over those as well. So let's just say I have a term over here. This is my magnitude, and this is my phase. So let's just say I have 1 plus 2 I omega C1 divided by tau 1 plus I omega divided by tau 1 squared. Repeat it n times. This basically tells me I have a quadratic 0. Right? Well, if I look at the magnitude, 20 times log 10 of the magnitude, again, I know it says 0, so it should go up. But remember, if I had a simple 0, it was going up by 20. But this quadratic 0 is basically 2 of those zeros multiplied by each other. Right? So what should I expect to get as my slope? It's 2 of those. So the slope should be multiplied by 2. Right? So I'm going to have a breakpoint at this tau 1, which is exactly this point that I have over here. And it goes up by 40 times N dB. If I look at the phase, with the exact same logic, this is 2 simple zeros multiplied by each other. They were complex, but they're still like zeros. So if I had like phase 45 degrees going up over there, over here, since it's like 2 of them, I should add them up. So it's 90 degrees. So it is tau 1 over 10, 10 tau 1. I have 0 degrees over here. And then over here, it's going to be 180 degrees times n. And in the middle, it is 90 times n degrees. Right? Remember, for the simple one, it was going up by 45 degrees. Over here, 90 degrees. And for the quadratic pole, it's very, very similar to this. So if I have something that looks like this, C1 over tau 1 plus I omega, just call it tau 2 squared power n. If I look at the magnitude, 20 times log 10 of the magnitude, again, I'm going to have like some breakpoint, which is this tau 2. And this time I'm going to go down by negative 40 dB. Right? And if I look at the phase is just this one flipped with respect to x-axis. Right? So it is tau 2 over 10, 10 tau 2. This is 0. This is negative 180 times n. And this is going to be negative 90 times n. Right? So as soon as I have these things, I can add them all up. Right? So let's quickly do an example. Let me just quickly go over like the recipe that we have as to how we can approximate this h. So how to approximate this absolute value of h and the phase of h, which we call the Bode. Step 1, we're going to rewrite the transfer function to look like the transfer function that we worked with. Basically, h of s equals k s to the power of plus or minus n, s over z1 plus 1 to the power of L1, 1 plus 2 C1, tau 1s plus s over tau 1 squared to the power of L2, s divided by P1 plus 1 to the power of H1, 1 plus 2 C2, tau 2s plus s over tau 2 to the power of 2 H2. Basically, what we're interested in doing is that we want to make sure that the constants that we have here, they're all 1. Right? We can do that. We can always do that by factoring it out. Right? As soon as I do this, the first thing I can do is that I can simply determine what my zeros are, what my poles are. Right? And why is that important for us to know where the zeros and poles are? Because I know if I want to approximate, the only time that I have a little change would be at the zeros or the poles. Otherwise, I'm not going to have any change. Remember like the breaking points? The breaking points only happening at either zeros or the poles. So as soon as I determine like what those are, I know exactly where these slopes are changing. Right? So the second step is to determine poles and zeros, and then use them as our breaking points. Now I know what kind of zeros I have, what kind of poles I have. I know what my breaking points are. I can use table 2 to approximate each term. So use table 2 to approximate each term. If I'm doing it for the magnitude, I'll do it on dB scale. And then I can like simply just plot the base, right? As soon as I have the plot for each term, I can add them up, add them all up, and get the approximation. Right? So let's try to apply this. Let's try to apply this to a function. Example. Let's just say h of omega is 10 times 0.1 I omega plus 1 divided by I omega plus 1 times 0.02 I omega plus 1. Right? The first step is to make this transfer function look like this. Remember, this S is I omega, right? How do I make this function look like this? Well, it is already like this. I just need to like play with it a little bit to determine exactly what my zeros and poles are, right? Do you agree I can write this h of omega as, well, this is a constant, I'm not going to change it, so I have this 10. I have this I omega. This is 0.1 times omega, which means 1 over 10 times I omega. So I'm going to write it as I omega divided by 10 plus 1, right? This I omega plus 1 is exactly the same as the thing I want. If I look at the coefficient of this I omega, it is 2 over 100. If I want to make the numerator 1, how do I do this? I'll take the 2 to the denominator, right? So I have to write it I omega divided by 100 divided by 2, right? What is 100 divided by 2? 50. So I can write this as I omega divided by 50 plus 1. Now, by looking at this, I know exactly what my zeros and poles are. So step 2. Let's look at the constant first. What is my constant? Well, the constant is 10, right? While we're at it, let's just find 20 times log 10 of that as well, to just get it out of the way. So I have 20 times log 10 of 10, which is what? What is log 10 of 10? 10 to the power of what is 10? 1. So log 10 of 10 is 1. So the whole thing over here is going to be 20 dB. Right? Now let's just look at our zeros and poles. Where is my 0? Well, I know this number down here represents my 0. So I know I have a 0 at omega equals 10. What kind of 0 is this? It's just simple 0, right? Simple 0 of order 1. So that's a simple 0. The poles. Well, I have 2 terms on the denominator, so I have 2 poles. One of them is happening at 1. The other one is happening at 50. So I have pole at omega equal to 1 and omega equal to 50. And both of them are simple. Right? Now I'm ready to plot. I know where the breaking points are, so I know where I'm going to have to change. So now we can plot 20 times log 10 of h of omega and the phase of h of omega. Right? Let's just say I have this omega. This is 20 times log 10 of absolute value of h of omega. Right? Keep that in mind. This omega increases as a power of 10. So let me just put it down. So this is basically 10 to the 0. This is 10 to the 1. This is 10 to the 2. And then 10 to the 3, and so on and so forth. Right? Let's just put down where the zeros and poles are. Because again, those are the points that I know I have some change right at that point. Right? Well, I know I have a pole at omega equal 1. 1 is 10 to the power of 0. So this is my pole 1. Right? I know I have a 0 at omega equal 10, which is 10 to the power of 1. So this is my 0. Right? And I know I have another pole at omega equals 50, which is somewhere in between. Right? So this is P2 equals 50. Right? If I want to plot this function, I have to plot 20 times log 10 of 10 plus 20 times log 10 of magnitude of this minus 20 times log 10 of magnitude of this minus 20 times log 10 of magnitude of this. Right? So let's just start plotting this 10. What was the 20 times log 10 of 10? That was 20 dB. So I have 20 dB. And it remains 20 dB. It remains at y equals 20 dB till I hit this first pole. Right? Remember, I'm adding them. As soon as I hit this 10 to the power of 0, which is 1, which I know it's a pole, what do I know? I know I'm going to go down by 20. So the slope here is going to be right at this point. It's going to be 20 down. And it's going to keep going down by 20 till I hit this 0. Right? As soon as I hit this 0, I know I have to go 20 up. Right? But I'm already going 20 down. So 20 down, 20 up. If I add them, what do I get? 0. So over here, as soon as I hit this, I'm going to have 0. And it stays at 0 till I hit my next 0 or pole. Well, in this case, it's a pole. What happens? I'm going to have to go down by 20. So I'm going to go down by 20. This is a piecewise approximation of the magnitude, 20 times log 10 of magnitude of h of omega. Right? Let's quickly look at the phase of this. Again, I know I have this whole 10 to the 0. I have this z 10 to the 1. I have this P2, which is 50. Right? So approximately the way it works is that for around this point, which is my pole, I have to go 45 degrees down. And for around this point, which is my 0, I have to go 45 up, right? So the way it works is that I have, well, I'm going to start at 0 because that's my k, right? Then for around this point, I'm going to go down by 45 degrees, right? For this z, I'm going to go up by 45 degrees, but I'm already going down, right? So it means 45 going down, 45 going up, so it's going to be 0, right? Till around this point that I know I'm going to go again 45 degrees down. And it basically evens out at negative 90 degrees, right? Because that's what it is, right? So it's not that bad. So this was a very simple example. Let's make it a little more interesting, right? Let's just say I want to plot this function. Example, I want to plot h of omega, which is I omega times I omega plus 100 divided by I omega plus 1 times negative omega squared plus 6I omega plus 400. Right? This is quite difficult function to plot, by the way. It's not a very simple function, right? But we're just going to approximate it by linear functions. What is the first step? We're going to have to make sure that we have this written in the form that we can actually utilize it. So the first step, we're going to have to rewrite this h of omega. Well, this I omega here is good, right? I know it's a simple 0 at the origin. I don't have to really change it. How about this one? I want to make sure the constant here is 1. So what I need to do is to factor out that 100. So if I do that, I have this 100 times I omega divided by 100 plus 1. This is exactly this function, right? I just need to distribute that 100 in there. This function over here, this I omega plus 1, is exactly the way I want. I don't have to do anything. This is a quadratic pole. So I have to execute a few things all together to be able to get it the way I want. First of all, I know I have to make this 400 1. So it means I'm going to have to factor out that 400. Right? The second thing is that I know to be able to plot it, the first term over here, that should be I omega divided by tau squared. Right? But that's negative omega squared. How do we do this? Remember, negative 1 is I squared. So negative omega squared is negative 1 times omega squared. Therefore, it's I squared omega squared. So I can rewrite the whole thing. So I'm going to factor out that 400. Then I'm going to write this as I omega divided by 20, the whole thing is squared. Remember, 20 times 20 is 400, right? So I already put it in the squared form. Plus 6 over 400 I omega plus 1. Now I got it the exact same way as I want, right? This is my constant. This is my constant k. And the rest is exactly what I want. So step 2, let's just find 20 times log 10 of the constant, which I know it's 20 times log 10 of 100 over 400. 100 over 400 is 1/4, right? And I know 20 times log 10 of 1/4 must be negative. Why is it negative? What is log of 1? 10 to the power what is 1? 0, right? So log of 1/4 is log of 1 minus log of 4. Therefore, it is minus log of 4, so it should be negative, right? And the 4 is like greater than 1. So this is basically negative 12 dB, right? Now let's look at the zeros and poles. What are my zeros? Well, I have a 0 at the origin, right? So I have a 0 at the origin. I have another 0 at 100, right? I have a pole at 1. And I have a quadratic pole that's happening at tau equals 20. So this is quadratic. This is simple. Both these are simple. You agree with me? Let's just plot it. So I'm going to look at omega, 20 times log 10 of absolute value of h. Again, remember this is 10 to the 0, 10 to the 1, 10 to the power of 2. Let's put down our zeros and 1 as zeros and poles. Right? What is my first 0? It's 0. How do I put 0 over here? That's a log scale. Where is 0 on a log scale? 10 to the power what is 0? Negative infinity. So there is no way for me that I can put this 0 on this x-axis, right? Nonetheless, I know I have a 20 dB going up from negative infinity, right? Because that's a 0 at 0. So let's table that for a second and work with things that we can actually put down over here, right? I have this omega equals 100, that's my 0. So this is my 0 over here, right? And then I have this simple pole over here, which is at this point, right? And then I have this quadratic pole that's happening somewhere here, right? Now let's plot. Keep that in mind. I have to plot every single term that I have. I know I have a simple 0 at the origin, so I know I'm going to start from negative infinity and go up all the way with the slope 20 dB, right? It is 20 dB because it's a simple 0 at the origin of order 1, right? So I'm going to have this going all the way up with slope 20 dB, right? But remember, this 20 dB that's going from minus infinity, that should be on top of this constant value that I have, because I'm adding it to that point. So it should be carried over this minus 12 dB, right? So it goes all the way here till it actually hits this point, which I know I have a pole. But remember, whatever I have here must be shifted by this negative 12. So this point over here is nothing but this negative 12 dB. Right? Everything is shifted by that negative 12. Right? Now life is normal. I hit a pole, I'm going 20 up. I have a pole, which means I'm going 20 down. What is my slope? 20 down, 20 up. What is the total? It's a 0. And it remains 0 till I hit my next 0 pole. I hit this tau. I know this tau is a quadratic pole. What does that tell me? It tells me I'm going down by 40. Right? So I'm going to go down by 40 till I hit the next 0 pole. In this case, I hit a 0. I'm going down by negative 40. I hit a 0, which means I have to go up by 20. So what is the total slope that I have here? It's negative 40 plus 20, which is negative 20. So it is negative 20 dB. Right? Does that make sense? We can do the reverse of this as well. I can give you this magnitude, and I can ask you, what is the transfer function? I can do that too. Let's do one example on that as well. Let's do one example on that as well. Example. Let's just say the magnitude, the 20 times log 10 magnitude of my transfer function looks like this. It looks like this. This is omega. This is 20 times log 10 of magnitude of h of omega. Let's just say this is 10 to the 0. This is 10 to the 1. And this is 10 to the 2. I have 5 over here, which I know I'm going to go down all the way here. Right? And this point corresponds to 0 dB. Right? And then I have 0 slope till this point 20. Then I'm going to go down by 20 till I hit this point 50. Right? Then I'll go constant till I hit this 10 to the power of 2, and then again go down by negative 20. And the question is, what is h of omega? Right? What is the first thing we notice here? What we notice is that we're coming from infinity till we actually hit this point 5. Right? And we're coming down by like negative 20 dB. What does it tell us? Doesn't it tell us that we have a simple pole at the origin of order 1? Doesn't it tell us? We're coming from infinity, right? And we hit this 5, right? So keep that in mind. We're going to use that fact in a second. Right? Actually, let's just use it right now before we forget. So I know for this line over here is k divided by some I omega. Right? What is this value at omega equal 5? That is 0 dB, right? It's not 0. So it's 0 dB. So 20 times log 10 of some number is 0. What is that number? 1. Right? So this number over here is 20 times log 10 of some number x equals 0 dB. Therefore, x must be 1. So I know k over I omega evaluated at this 0.5 is 1. Do you agree with that? Yes or no? Remember, like these functions just be on top of each other and they get added to each other. So if I wanted to plot this, I have to plot 20 times log 10 of this plus 20 times log 10 of this 1 over I omega. But I know this 1 over I omega that comes from infinity till it hits this 0.5. And that 0.5 over here, that tells me this k. Just like the previous example we did. Right? But this number is 0 dB on a linear scale. It is just 1. Right? Because 20 times log 10 of something is 0. And that something must be 0, must be 1. So I know k over this I omega, evaluated at 5, must be 1. What is k then? This tells me k over 5 equals 1. Therefore, k is 5. Right? You with me so far? Right? The rest is pretty simple. Why? I only need to look at these breaking points. I need to look at 5, 20, 50, and 100. Right? And evaluate them and just see like what type of zero or pole they are. Look at this 5. I'm going down by 20, but right after this 5, the slope is 0. What does it tell me? It tells me this 5 must be a simple 0 of order 1. Right? So we know at omega equals 5, we have a simple 0, which we can write it as I omega divided by 5 plus 1. Right? Now we don't have any change till we actually hit the next breaking point, which is this 20. This 20 tells me I'm going to go down by 20 dB. What does it tell me about this 20? That's a simple pull, right? So we know at omega equals 20, we have a simple pull. So I can write it as 1 over I omega divided by 20 plus 1. Right? Again, nothing changes till I hit this 50. right? At 50, I have a slope of 0. What does that tell me? I was going down by 20, but the slope is 0. It means that 50 over here must have been a simple 0. So at 50, we have a simple 0, which we can write it as I omega divided by 50 plus 1. Again, nothing changes till I hit this 100. So at omega equals 100, I was going by 0, but I have a decay here. So it tells me it should be a pole, right? So we have a simple pole. So we can write it as I omega divided by 100 plus 1 to the power of negative 1. It's 1 over that, right? Just trying to save some space. That's why I wrote it this way, right? And then I'm done. What is my h of omega? All these things multiplied, right? All of them multiplied. So I have h of omega. It is 5 over I omega times I omega over 5 plus 1 divided by I omega over 20 plus 1 times I omega divided by 50 plus 1 divided by I omega over 100 plus 1. Right? You with me? Yeah? Again, I only pay attention to the zeros and poles, right? And if I have something that's coming from negative infinity with this slope 20, it means it should be a simple 0 at the origin. If it's something that's coming from negative infinity, but with the negative slope, it means there has to be a simple pole at the origin, right? Let's do another example. Example. Let's just say I have a circuit that looks like this. Vn of t is u of t, which means it is 1 for time greater than 0. For time less than 0, it is 0. I have a 1 ohm resistance here, another 1 ohm resistance here, another 1 ohm resistance here, and I have a 1 farad capacitor over there, and this is V out. Yes.
Did you say your voltage was?
The input is u of t, a step function. So it looks like this. It's 1 for all times greater than 0, and it is 0 for time less than 0. It's basically a switch, right? We're going to talk about this in a lot more detail when we're talking about Laplace transform, right? At the moment, that's not our concern. Our concern is that what is V out over Vs, V in, right? And I'm going to tell you the Laplace transform of V in of t is 1 over s. Basically, if we go from time domain to the s domain, it is 1 over s, right? The question is, what is V out of s to the V in of s? And how can we plot it, right? How do we do this? Well, to be able to find the transfer function, we always have to go from time domain to the frequency domain, right? In this case, we're going to go to S domain, which is the similar thing, right? Remember, S is I omega. So I'm going to go to the S domain. I know I have to convert this to the S domain, which I know it is 1 over S. This resistance would not change. This one would not change either. This would not change either. If I have a capacitor, the capacitor changes to 1 over I omega C, right? Let's just write it as 1 over SC, right? Which is 1 over S. And I have to find this V out of S, and this is V in of S, right? Do you agree I can combine these two and then the result with this one? Do you agree I can do that? So Z equivalent is this 1 over S plus 1 in parallel with 1. Right? Which I can write it as, let's simplify this. This is S plus 1 divided by S. So it is S plus 1 divided by S times 1 divided by S plus 1 divided by S plus 1. So it is S plus 1 divided by S, 2S plus 1 divided by S. S and S cancel. So it is S plus 1 divided by 2S plus 1. Right? Do you agree I can find voltage across the equivalent here? Do you agree with that? Yes or no? I can find the voltage across the equivalent. What is the voltage across the equivalent? Remember, my circuit is this. This Vn of S, which is 1 over S. This is 1. This is this Z equivalent. What is voltage across this? What type of circuit do I have? It's a voltage divider, right? So I have Z equivalent of S divided by 1 plus Z equivalent of S times Vn of S. Right? Do you agree this V equivalent is voltage across this one, and it's also voltage across these two? Yes? If I know voltage across these two, what is V out then? What is it? It's 1 over S divided by 1 plus 1 over S times V equivalent of S. Right? I know this V equivalent, so it is, let me just simplify this. So it's 1 over S divided by S plus 1 divided by S. This and this cancel. So I have 1 over S plus 1 times V equivalent, which is this Z equivalent, S plus 1 divided by 2S plus 1 divided by S plus 1 divided by 2S plus 1 plus 1 times V in of S. Right? I just replaced this V equivalent by this. Right? Let's simplify it a little bit. I can write this as S plus 1 divided by 2S plus 1 divided by S plus 1 plus 2S plus 1 divided by 2S plus 1. Right? So this and this cancel. So the whole thing over here is S plus 1 divided by 3S plus 2. This S plus 1 cancels this S plus 1. So my V out of S is 1 over 3S plus 2 times V in of S. Right? What is V out of S divided by V in of S? That's this 1/3S plus 2. Right? So this is my transfer function. Right? I can plot it. Right? Remember, S is I omega. So H of omega is V out of omega divided by V in of omega, which is 1/3 times I omega plus 2. How do we plot it? Well, again, I want this coefficient to be 1, so I'm going to factor it out. So I have 1/2 times 3 half I omega plus 1. Right? Right? Where's my pole? Remember, I have to write this in terms of 1/I omega P1 plus 1. So what is my P1? It's 2/3, right? So P1 is 2/3. My constant K is half. Right? I can plot it. Right? If I plot it, it's 20 times log 10 of magnitude of H of omega. I know I have a break at this P1, which is 2/3. Right? I'm going to have 20 times log 10 of magnitude of half over here till I actually hit this point where I go down by 20 dB. Right? What kind of filter is this? It's a low pass filter, right? It keeps low frequencies and rejects higher frequency. So this is a low pass filter. If I wanted to check if this is exactly like a low pass filter, how would I check it? I have to look at this transfer function when omega is like small, right? And that magnitude must be around 1. And if I look at higher frequency, the magnitude must be around 0. So let's check it out that way so we get some practice as well. So H of omega is 1/2 plus I 3 omega. So if I look at the magnitude of H of omega, it is 1/square root of real part squared, so it's 4, plus 9 omega squared. Right? So what is H of omega when omega is 0? I have to put omega 0, right? So it's 1/2. Right? So it has some values. Right? What is the magnitude of H of omega when omega approaches infinity? What is it? When omega approaches like infinity, this term dominates. So this is like 1/3 times omega. So this approaches 0. So this is 0. Which again, it verifies our graph, which we know it was a low pass. So this is a low pass. So if I give you like this circuit on the exam, and I ask you like, what type of filter is this? And plot the filter, you should be able to do it, right? You're going to look at the transfer function, right? You're going to see like how that circuit behaves around omega 0, how it behaves for very large omegas, and that determines like what type of filter you have. And since we just learned about the Bode plot, we can always approximate that function, just like what we did in this example. All right? Any question? Is this clear what we're doing? Does that make sense? All right, I'll see you guys Monday.